Okay, so another video started here. I should have broken it up again earlier, but whatever. So tree traversals. How do we go through this tree anyway? Because if you're just looking at it and you want to, so say we've got a tree like this. So 50, 25, 100, 50, 25, 75, 100, 10, 35 over here, 40, 30, right? All these nodes over here, right? How would I even go about printing out all the values in here, right? Suppose I have this this tree that I've drawn up here, right? How would I go about even printing out all the values in this tree in a meaningful way, right? And this question is called how do I traverse this tree? Is kind of the technical term. How do we traverse it? How do we go through it? And there's 4 ways technically. We're going to learn about in-order, post-order, pre-order. Remember, infix notation, postfix notation, prefix notation. This is relevant. But also there's a 4th way, which is height-based, which is simply which we won't learn here, which is start at this one, then go through. So go through level 1, then go through all the nodes on level 2, then go through all the nodes on level 3, and then all through all the ones on level 4, which would really be easier if I actually could draw and make sure that all the things on level 3 were the same level. So the question is, how do I go through all these trees? How do I walk through the tree? Okay, and we have 3 ways, which is in order, pre-order, post-order. In order is the most common way to do things because it's the way because that will produce stuff in the sorted order. Okay, so in order is going to give you stuff in the actual order that data should be in the tree. So it's going to give you, if you're storing a bunch of numbers, it will give you all the numbers. So if I did an in-order traversal of this tree, it's going to do 25, 30, 35, 40, 50, 55, 75, 100, right? All the stuff in order. Pre-order will basically, and post-order really won't have a numerical sense, but they will give you a better hierarchical understanding, or pre-order will. And post-order, it's a bit different. But they're all the same algorithm, actually. They all actually are the same method. They just switch the recursive calls are just simply appear in a different order. Remember how when we were talking about doing the remember how when we did the recursion string, the recursive print method a while back, that might have just been last week actually. Remember how we did that? How basically just by flipping the line in the recursive print method, it went from printing everything in order to printing everything in reverse. Yeah, this is exactly what's going on there. By switching the order of the recursive calls, we can actually do a bunch of different things. So we'll start with the middle one, which is in order, which will produce everything being stored in the proper order. So to do a pre-order traversal, we first do an in-order traversal on the left tree. We then visit the root node, and then we'll do an in-order traversal on the right tree. Or if we're aiming to print stuff, essentially this says recursively print out all the stuff in the left tree, print out my thing, then recursively print out all the stuff on the right. Or to translate that again, print out all the stuff that's less than me, print out myself, print out all the stuff that's greater than me, but do so recursively. So printing out all the stuff to the left of me, well, we'll go visit to the left, and the left subtree will go, well, print out all the stuff in my left subtree, print out myself, then print out all the stuff in my right subtree, which is all the stuff bigger than me, right? So let me go ahead and clean up the this a bit because let me clean this up a bit so it's actually balanced. 25, 60, 100, 45, and let's go with 20. So we'll go with this example. So for an in-order traversal, what do? I visit my left side first, and then I'll handle myself. So right now we'll say we're going to print out the left side. Well, he goes, well, I'm going to print out my left side first, then I'll print out myself, then I'll print out my right. So we go over here. He says, I'll print out my left side first. Well, that's empty. Okay. I'll print out myself, then I'll print out my right side. Okay. So 25 goes, well, I finished printing out my left side, so I'll print out myself. Now let me print out my right side. And he'll go, well, let me print out my left side. Okay, I'm done. Print out myself. Print out my right side. There's nothing there. And then 50 finally goes, okay, so 25 finished. Sorry, so 45 goes, I'm done. 25 goes, I'm done. 50 goes, my left side is done. So let me go ahead and print out myself. And then I'll print out my right side. Who goes, let me print out my left. Then, okay, my left side's done. I'll print out myself. Let me print out my right side. Okay, and then he goes, aha, I'm done printing out my right side, so we're done. And so 50 goes, okay, I'm completely done, we're done. Okay, so that's in order, right? Print out the stuff to your left, print out myself, print out my right side. And it's completely recursive. Okay? On the other hand, so again, it was left, myself, right. So for all the other stuff, it's just a matter of switching up the order there. So pre-order means rather than going to my left, then myself, then my right, I'm going to be selfish and print myself first. Then I'll do my left, then I'll do my right. Okay? And post-order is I'll be selfless. I'll do my children first, then I'll do myself. And notice that the left comes before the right, so there's only 3 possible combinations. Does handling myself come before my children, in between my children, or after my children? Right? And since left always goes to the right. So as you can see here, right, the algorithm, if my tree is empty, return. So for in order, traverse the left, visit the root, in order, traverse the right. So notice that basically the only thing that changed is the prefix, right? Pre-order, in order, post order, and what order does visit the root command come in? Does it come in line 3, line 4, or line 5? It's the same algorithm, just arranged different ways. So this is the traversal algorithm. This is one of the ones that solve 90% of the tree problems out there. Okay, so how does the pre-order look then? What does a pre-order rendering of this look like then? It's going to look like this. I'll do myself, then I'll do my left, and then my right. Okay, so let's do my left. Well, he goes, I'll do myself, then I'll do my left, then I'll do my right. 20 goes, I'll print out myself. So 25 goes, I'll print out my right now. So I'm done printing out my left. 50 goes, I'm done printing out my left side. So now I'll print out my right side, which will go 75, 60, right? 75, then it goes left and then my right. Okay, so it doesn't really tell you too much about about the data stored in the tree, really, unfortunately. But with some clever, you can turn this into a nice two-string method with some clever indenting, and basically indent stuff basically every time you go down a level, so that you can kind of see a hierarchical data structure. So it's pretty nice, but otherwise it's just, you know, a way to iterate through things and make sure you're going. I mean, it's useful for producing the basically the order of the tree, because it's going to be myself, then my children, and then my other children, right? So here's me, and there's the left tree, and then there's the right tree over there. So the structure is kind of preserved there, which is nice. What about post order? Well, post order says I'm going to print out my right side, then my left side, then my right side, then myself. So 50 goes, print out my left side, then my right side, then myself. 25 goes, print out my left side, then my right side, then myself. So 20, 45, 25. Then 50 goes, print out my right side. 75 goes, print out my left side, my right side, then myself, and then 50. You might be wondering what the heck is this for. All shall eventually be revealed. And there's the root. But those are just the different ways of going through these trees. Yes, is that a question?
Yeah, if you're adding data to it, how do you determine what the head node is?
What the root node is? The root's always going to is always the first node you added to the tree.
And then it just goes.
And then that's it. It's always going to be the first node is always the root. It's never going to change. The root's never going to change unless you remove the root, unless you have, or rather delete it. And the reason for at least in the binary search trees we're learning. If, on the other hand, we are dealing with a self-balancing binary search tree, it will rearrange itself to whatever should most optimally be the root. So went through that. So what's cool about this is that if we can create these things called and this will be the last thing before I let you guys go. So we can have these things called expression trees, where basically we take algebraic expressions, right? And that was all the way back at the beginning of this thing. Too far, right? So all the way back here, we were talking about expression trees. There was a slide about expression trees, which was that every node contains either an operator or an operand. The operands, in other words, the actual variables and stuff, are stored in the leaves, and all the operators are internal nodes. We don't preserve, and when you store an expression like this, you don't need parentheses because it's implied, right? It's x plus y times the result of doing a plus b divided by c, right? It's stored in there. Okay, so how does this get into our prefix postfix kind of thing? Well, an in-order traversal of this tree will give you x plus y times a plus b divided by c, which is the expression that's being stored in there, minus all the parentheses, right? Right? So we don't know how to evaluate this without the parentheses. Yes? What goes left and right? X plus y times... We're saying we aren't caring about how to generate this. We're saying, given this tree, if we do an infix traversal of this, we'll get this expression, right? Which, again, we get all the imperfections of an infix notation, which is that basically we need parentheses to parse it. Yes.
So before when you said objects had to be comparable, that doesn't apply right now.
Yeah, this is just a binary. Yeah, this is just a binary tree over here. I don't know why it says binary search trees, because honestly, there's a binary tree over here. But now if we do because we can do traversals on any kind of tree. But now if we do a post-order traversal, we'll get the postfix notation out of it. So post-order traversal will basically be, okay, so go to the left, x, y plus, right? So we're adding x and y. So add x and y to the stack, then plus, then add the combination back into the stack, right? And then AB. So it gives you so by parsing this expression tree, we get the unambiguous postfix notation. Okay? Or reverse Polish form, as we called it. And if you do it in the prefix order, you get the prefix order, the other unambiguous form. Where basically we want to multiply these two arguments. Plus, the first argument is plus xy, and the second argument is the division of adding a and b together and dividing that by c. Right? So again, these are both basically unambiguous ways to do stuff, although it's easier for us to use a stack to parse that out. So when we get back, we'll briefly review. So when we get back from spring break, we're going to briefly review this stuff. And we'll talk about how do we implement a binary tree in class. If I'm feeling really adventurous, then what I might do is I might instead pre-record this entire lecture of how do we build a binary tree and post it online for you guys and I'll send an email out, an announcement well in advance telling you, hey, you should totally watch this lecture before you come on Tuesday, because on Tuesday we'll do something in class instead. Right, we'll do an exercise in class, because honestly, watching me build data structures, it will give you a better understanding of how it works, but it's kind of boring, right? I mean, I try to keep it as entertaining as possible, but there's only so much entertainment value we can derive from this. So I hope you guys do enjoy your spring break, though. And I, don't want you guys to make sure you don't go too crazy doing a bunch of work or avoiding it either. So, okay. Thanks.